ਤੁਸੀਂ ਸ਼ਾਇਦ ਜਾਣਦੇ ਹੀ ਹੋ ਕਿ ਵੇਵਸ ਨਾਲ ਸਾਡਾ ਵਾਹ ਰੋਜ਼ਾਨਾ ਜੀਵਨ ਵਿੱਚ ਆਮ ਹੀ ਪੈਂਦਾ ਰਹਿੰਦਾ ਹੈ। ਵੇਵਸ ਸਾਡੇ ਹਰ ਪਾਸੇ ਮੌਜੂਦ ਹਨ। ਸਾਊਂਡ ਵੇਵਸ, ਵਿਜ਼ੀਬਲ ਲਾਈਟ ਵੇਵਸ, ਰੇਡੀਓ ਵੇਵਸ, ਮਾਈਕ੍ਰੋਵੇਵਸ, ਵਾਟਰ ਵੇਵਸ ਅਤੇ ਵੇਵਸ ਔਨ ਸਟ੍ਰਿੰਗ ਵੇਵਸ ਦੇ ਕੁਝ ਆਮ ਉਦਾਹਰਣ ਹਨ। ਇਨ੍ਹਾਂ ਵੇਵਸ ਨੂੰ ਸਿੰਪਲ ਹਾਰਮੋਨਿਕ ਮੋਸ਼ਨ ਦਾ ਐਗਜ਼ਾਮਪਲ ਮੰਨਿਆ ਜਾ ਸਕਦਾ ਹੈ। ਅੱਜ ਅਸੀਂ ਇਨ੍ਹਾਂ ਤੇ ਹੀ ਵਿਚਾਰ ਕਰਾਂਗੇ।
Dear students, welcome to today's lesson of simple harmonic motion. Let me start with telling you the learning objectives for today's lesson.
On completion of this topic, learners will be able to define periodic motion and time period, discuss oscillatory motion, discuss the basic terms related to simple harmonic motion, discuss periodic motion, discuss uniform circular motion and simple harmonic motion.
ਇਹ ਤਾਂ ਅਸੀਂ ਸਾਰੇ ਹੀ ਜਾਣਦੇ ਹਾਂ ਕਿ ਸਾਡੇ ਆਲੇ ਦੁਆਲੇ ਦੇ ਆਬਜੈਕਟਸ ਵਿੱਚ ਡਿਫਰੈਂਟ ਟਾਈਪਸ ਆਫ ਮੋਸ਼ਨ ਦੇਖਣ ਨੂੰ ਮਿਲਦੀਆਂ ਹਨ। ਅਸੀਂ ਇਹ ਵੀ ਜਾਣਦੇ ਹਾਂ ਕਿ ਕਿਸੇ ਮੂਵਿੰਗ ਆਬਜੈਕਟ ਦਾ ਮਤਲਬ ਹੈ ਸਮੇਂ ਦੇ ਨਾਲ-ਨਾਲ ਇੱਕ ਫਿਕਸਡ ਰੈਫਰੈਂਸ ਪੁਆਇੰਟ ਦੇ ਕੰਪੈਰੀਜ਼ਨ ਵਿੱਚ ਇਸ ਦੀ ਪੋਜੀਸ਼ਨ ਵਿੱਚ ਚੇਂਜ। ਪਰ ਤੁਸੀਂ ਕਦੇ ਨਾ ਕਦੇ ਕੁਝ ਵਸਤਾਂ ਦੇ ਮੂਵਮੈਂਟਸ ਇਹੋ ਜਿਹੇ ਵੀ ਦੇਖੇ ਹੋਣਗੇ ਜਿਨ੍ਹਾਂ ਵਿੱਚ ਇਸ ਦੀ ਪੋਜੀਸ਼ਨ ਕੰਪਲੀਟਲੀ ਚੇਂਜ ਨਹੀਂ ਹੁੰਦੀ, ਬਲਕਿ ਇੱਕ ਖਾਸ ਫਿਕਸਡ ਪੈਟਰਨ ਵਿੱਚ ਹੀ ਆਪਣੇ ਆਪ ਨੂੰ ਦੁਹਰਾਉਂਦੀ ਰਹਿੰਦੀ ਹੈ। ਮਸਲਨ ਇੱਕ ਸੀਸੋ ਜਾਂ ਆਮ ਝੂਲਾ, ਹਵਾ ਨਾਲ ਹਿਲਦੇ ਕਿਸੇ ਦਰਖਤ ਦੇ ਪੱਤੇ ਜਾਂ ਟਾਹਣੀਆਂ ਅਤੇ ਇਸ ਤਰ੍ਹਾਂ ਦਾ ਬੜਾ ਕੁਝ ਹੋਰ। ਇਹਨਾਂ ਵਿੱਚੋਂ ਜ਼ਿਆਦਾਤਰ ਹਾਲਤਾਂ ਵਿੱਚ ਆਬਜੈਕਟ ਆਪਣੇ ਆਲੇ ਦੁਆਲੇ ਟੂ ਐਂਡ ਫਰੋ ਮੋਸ਼ਨ ਅਬਾਊਟ ਅ ਸੈਂਟਰਲ ਪੋਜੀਸ਼ਨ ਵਿੱਚ ਨਜ਼ਰ ਆਉਂਦਾ ਹੈ। ਇਸ ਸੈਂਟਰਲ ਪੋਜੀਸ਼ਨ ਨੂੰ ਆਬਜੈਕਟ ਦੀ ਮੇਨ ਪੋਜੀਸ਼ਨ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। In this lesson today, we will define and describe this kind of motion. A motion which repeats itself over and over again after a regular interval of time is called a periodic motion. To give you an idea about this kind of motion, let me show you some examples.
ਤੁਸੀਂ ਸਾਰੇ ਇਹ ਜਾਣਦੇ ਹੋ ਕਿ ਚੰਨ ਧਰਤੀ ਦੁਆਲੇ ਸਰਕੂਲਰ ਆਰਬਿਟ ਵਿੱਚ ਘੁੰਮਦਾ ਹੈ ਅਤੇ ਇਸੇ ਤਰ੍ਹਾਂ ਧਰਤੀ ਤੇ ਚੰਨ ਦਾ ਕੰਬਾਈਨਡ ਸਿਸਟਮ ਸੂਰਜ ਦੁਆਲੇ ਇਲਿਪਟੀਕਲ ਆਰਬਿਟ ਵਿੱਚ ਘੁੰਮਦਾ ਹੈ। ਇੰਨਾ ਹੀ ਨਹੀਂ, ਧਰਤੀ ਅਤੇ ਚੰਨ ਆਪਣੇ ਧੁਰੇ ਦੁਆਲੇ ਸਪਿਨ ਵੀ ਕਰਦੇ ਹਨ। ਇਹ ਸਾਰੇ ਫਿਕਸਡ ਟਾਈਮ ਇੰਟਰਵਲਸ ਤੋਂ ਬਾਅਦ ਆਪਣੇ ਆਪ ਨੂੰ ਰਿਪੀਟ ਕਰਦੇ ਹਨ। ਧਰਤੀ ਇਲਿਪਟੀਕਲ ਆਰਬਿਟ ਵਿੱਚ ਸੂਰਜ ਦੁਆਲੇ ਲਗਾਤਾਰ ਵਾਰ-ਵਾਰ ਚੱਕਰ ਲਗਾਉਂਦੀ ਰਹਿੰਦੀ ਹੈ ਅਤੇ ਇਸ ਦਾ ਇੱਕ ਚੱਕਰ 1 ਸਾਲ ਵਿੱਚ ਪੂਰਾ ਹੁੰਦਾ ਹੈ। ਫਿਰ ਤੁਸੀਂ ਜਾਣਦੇ ਹੀ ਹੋ ਕਿ ਫੇਜ਼ਸ ਆਫ ਮੂਨ ਵੀ ਆਪਣੇ ਆਪ ਨੂੰ ਹਰ 28 ਦਿਨਾਂ ਬਾਅਦ ਰਿਪੀਟ ਕਰਦੇ ਹਨ।
ਹੈਲੇਜ਼ ਕੋਮੇਟ
ਸਾਡੇ ਸੋਲਰ ਸਿਸਟਮ ਦਾ ਹੀ ਮੈਂਬਰ ਹੈ ਅਤੇ ਸੂਰਜ ਦੁਆਲੇ ਘੁੰਮਦਾ ਹੈ। ਅਸੀਂ ਇਸ ਨੂੰ ਹਰ 76 ਸਾਲਾਂ ਬਾਅਦ ਧਰਤੀ ਤੋਂ ਵੇਖ ਸਕਦੇ ਹਾਂ। ਇਸੇ ਤਰ੍ਹਾਂ ਜਦੋਂ ਇੱਕ ਪੈਂਡੂਲਮ ਦੇ ਬੌਬ ਨੂੰ ਆਪਣੀ ਮੇਨ ਪੋਜੀਸ਼ਨ ਤੋਂ ਡਿਸਪਲੇਸ ਕਰਕੇ ਕਿਸੇ ਇੱਕ ਐਕਸਟ੍ਰੀਮ ਤੱਕ ਲਿਜਾਇਆ ਜਾਂਦਾ ਹੈ ਤਾਂ ਉਸ ਵਿੱਚ ਇੱਕ ਟੂ ਐਂਡ ਫਰੋ ਮੋਸ਼ਨ ਸ਼ੁਰੂ ਹੋ ਜਾਂਦਾ ਹੈ, ਜਿਹੜਾ ਪੀਰੀਓਡਿਕਲੀ ਵਾਰ-ਵਾਰ ਰਿਪੀਟ ਹੁੰਦਾ ਰਹਿੰਦਾ ਹੈ।
Let me now define the oscillatory motion for you. A motion that repeats itself over and over again about its mean position such that it remains confined within two well-defined limits called extreme positions on either side of the mean position is called an oscillatory motion or vibratory motion. Thus, a bounded and periodic motion of a particle about its mean position may be called as an oscillatory motion. Thus, all oscillatory motions are periodic, but all periodic motions are not oscillatory. Among the motion of the Earth, Halley's comet, phases of moon, and the bob of a simple pendulum, only the motion of the bob of simple pendulum is oscillatory motion. However, all of them are periodic motions. Let me show you a real-life example of oscillatory motion.
Consider a stone thrown in a pond in which a plastic bottle is lying over the surface of water. As the stones strike the surface of water, a large number of ripples appear at the surface of water. Due to the formation of ripples, the bottles start oscillating till the ripples are formed in the pond.
We will now get on to learn some basic terms related to periodic motion and oscillatory motion. I will start with the term time period. The time taken in completing one full oscillation or vibration is called its time period or simply the period. It is usually denoted by capital T. Let's try to understand this definition of time period through an animation.
Let us consider the motion of the bob of a simple pendulum. Initially, the bob of the pendulum is at the mean position O. Suppose that the bob is taken to the right extreme position A and then released. The bob passes over the mean position O, goes to the left extreme position B, and then returns back to the mean position O. It now moves to the right extreme and again returns back to the mean position. A to and fro motion sets in. The motion executed by the bob from point O to B, then to A via O, and then back to point A is said to be one complete oscillation. The time t in which this one oscillation is completed is called the period of the bob.
The SI unit for measuring time period is second. However, for two slow motions, it may be conveniently measured in minutes, hours, days, or even in years. For two fast motions, a convenient unit of time such as a microsecond, which is equal to 10 raised to the power minus 6 seconds, or a nanosecond, which is equal to 10 raised to the power minus 9 seconds, may be used. The number of the oscillations that occur in a unit time is called the frequency of the periodic motion. It is denoted by a symbol nu, and nu is equal to 1 by t. Usually, the frequency of a periodic motion is measured as the number of vibrations completed in 1 second. Therefore, the unit of frequency is per second or hertz. The frequency of a vibrating body is said to be 1 hertz if it executes 1 vibration per second or 1 cycle per second. The next term we will define is the amplitude. The maximum displacement of the oscillating particle from its mean position to either of its extremes is called its amplitude. The amplitude may not always be a linear distance from the mean position of the oscillating particle.
In the motion executed by a loaded spring, the amplitude is a linear distance. When the bob of a simple pendulum oscillates, the amplitude is angular in nature. When sound propagates through air, the change in the value of pressure at a point is treated as amplitude.
In addition to these examples, in the propagation of electromagnetic waves, the change in electric and magnetic fields are termed as amplitudes. Thus, in physics, the amplitude in a periodic motion represents change of some measurable physical and magnetic field, current, voltage, etc. In general, amplitude is represented by the Greek letter xi. However, the displacement of an oscillating particle may be denoted by x or y depending upon whether the displacement is along the direction of x-axis or y-axis. We are now going to know about periodic functions, a short discussion of which is necessary to be taken up before studying simple harmonic motion. Suppose periodic motion is represented by the sine or cosine function of the time variable t. That is, ft is equal to sine 2 pi by capital T into t as equation 1 and gt equal to cos 2 pi by capital T into t as equation 2. Here, capital T is the time period of the periodic motion. We can check if both the functions repeat themselves after a time period capital T. It will be so if the same function is obtained when the variable t is changed to t plus capital T in equation 1. Replacing t by t plus capital T in equation 1, we have ft plus capital T is equal to sine 2 pi by capital T into whole t plus capital T, which is equal to sine 2 pi by capital T into t plus 2 pi, representing equation 3. Using sine theta plus 2 pi is equal to sine theta in equation 3, we get ft plus capital T equal to sine 2 pi by capital T into t as equation 4. Now comparing equation 1 and equation 4, we get ft plus t is equal to ft as equation 5. Similarly, by replacing t by t plus capital T in equation 2, we can prove that gt plus capital T is also equal to gt as equation 6. Further, for the functions defined by the equations 5 and 6, it can be easily verified that ft plus n capital T is equal to ft and gt plus n capital T is equal to gt. Let this be equation 7, where n is equal to 1, 2, 3 and so on. A few more useful periodic functions can be constructed in terms of sine and cosine functions, which can be written as fnt equal to sine 2 pi n by capital T into t, representing equation 8, and gnt equal to cos 2 pi n by capital T into t as equation 9, where n is equal to 1, 2, 3 and so on. The functions given by equations 8 and 9 define different periodic functions for different values of n. It can be verified that for any value of n, fnt plus capital T is equal to fnt and gnt plus capital T is equal to gnt. Any periodic function with period capital T can be represented as a linear combination of functions described by the equations 8 and 9. Let us consider this function ft equal to sigma over n is equal to 0 to infinity of an into cos 2 pi by n by capital T into t plus bn into sine 2 pi n by capital T into t, where n varies from 0 to infinity. This is equation 10. For n is equal to 0, ft is equal to a naught. Since a naught is a constant function, it is periodic for any value of capital T. Similarly, we can evaluate the function ft for n is equal to 1, 2, 3 and so on. It follows that the equation 10 represents a linear combination of the periodic functions for n equal to 1, 2, 3 and so on. The function ft given by equation 10 can be expanded as ft equal to a naught plus a1 cos 2 pi by capital T into t plus a2 cos 4 pi by capital T into t plus so on up to plus b1 sin 2 pi by capital T into t plus b2 sin 4 pi by capital T into t plus so on, representing equation 11. The expression given by equation 11 is called the Fourier series, and the coefficients a0, a1, a2 and so on, b1, b2, b3 and so on are called the Fourier coefficients. A periodic motion for which the Fourier coefficients a1 and b1 both are not equal to 0 is called a simple harmonic motion. Thus, a simple harmonic motion is represented by the periodic function ft is equal to a1 cos 2 pi by capital T into t plus b1 sin 2 pi by capital T into t. There are no physical examples of absolutely pure simple harmonic motion. It may be pointed out that ft represents the displacement of the periodic motion at any time t. As we have learned that a simple harmonic motion can be represented by the function ft is equal to a1 cos 2 pi by capital T into t plus b1 sin 2 pi by capital T into t as equation 1. However, by proper choice of the coefficients a1 and b1, the simple harmonic motion can be expressed by a periodic function in several convenient forms. Suppose that a1 is equal to a cos phi and b1 is equal to minus a sin phi, which is equation 2. On squaring and adding the terms in equation 2, we get a1 square plus b1 square equal to a square into cos square phi plus a square into sin square phi. On simplifying, we get a1 square plus b1 square equal to a square. This implies a is equal to under root a1 square plus b1 square. Also, tan phi is equal to minus b1 by a1, or phi is equal to tan inverse minus b1 by a1, which is equal to minus tan inverse b1 by a1. Now substituting the values of a1 and b1 from equation 2 in the equation 1, we get ft is equal to a cos phi into cos 2 pi by capital T into t minus a sin phi into sin 2 pi by capital T into t, which is equal to a into whole of cos phi into cos 2 pi by capital T into t minus sin phi sin 2 pi by capital T into t. On simplification, we get ft is equal to a into cos 2 pi by capital T into t plus phi, which is equation 3. Now suppose that a1 is equal to a sin phi and b1 is equal to a cos phi as equation 4. On squaring and adding both the terms of equation 4, we get a1 square plus b1 square is equal to a square into sin square phi plus a square into cos square phi. On simplifying, we get a1 square plus b1 square is equal to a square. This implies a is equal to under root a1 square plus b1 square. Also, phi is equal to tan inverse a1 by b1. Substituting the values of a1 and b1 from equations 4 in equation 1, we get ft is equal to a sin phi cos 2 pi by capital T into t plus a cos phi sin 2 pi by capital T into t, which is equal to a into whole of sin phi into cos 2 pi by capital T into t plus cos phi into sin 2 pi by capital T into t. On solving this, we get ft equal to a sine of whole of 2 pi by capital T into t plus phi as equation 5. Both the equations 3 and 5 are used to represent simple harmonic motion. Finally, we can make two important conclusions about simple harmonic motion. 1. Ft gives displacement of simple harmonic motion at any time t. Secondly, as maximum value of sine or cosine of a function is 1, it follows that maximum value of the amplitude is A. In the equations 3 or 5, 2 pi by capital T into T plus phi is called the phase at time t, if phi is changed to phi plus pi by 2. In the function of equation 5, we obtain the function as in equation 3. Thus, simple harmonic functions in equations 3 and 5 are not different. They only differ in phase by pi by 2. Further, 2 pi by capital T equal to omega is called the angular frequency. Therefore, the equations 3 and 5 may be written as Ft equal to A cos omega t plus phi and Ft is equal to A sin omega t plus phi. You will be able to feel more confident about these relations if you are helped to solve a numerical problem based on the concept of simple harmonic motion. A simple harmonic motion is represented by Ft is equal to 10 into sin 20t plus 0.5. Write down its amplitude, angular frequency, time period and initial phase if displacement is measured in meters and time in seconds. Here, the equation of simple harmonic motion is given by Ft equal to 10 into sin 20t plus 0.5 representing equation 1. Let us compare the above equation with the general equation representing simple harmonic motion, that is Ft is equal to A sin of omega t plus phi representing equation 2. Now, comparing equations 1 and 2, we get the amplitude A is equal to 10 meter and angular frequency omega is equal to 20 radian per second. Now, frequency nu is equal to omega by 2 pi, which is equal to 20 by 2 into 3.14 equal to 20 by 6.28, which turns out to be 3.18 Hertz. Also, the time period capital T is equal to 2 pi by omega equal to 2 into 3.14 by 20, which is equal to 6.28 by 20. This becomes equal to 0.314 second. Also, by comparing equations 1 and 2, we get the initial phase as phi equal to 0.5 radian. While discussing simple harmonic motion, a study of uniform circular motion becomes a necessary part of it. I will like to show you an example that will give you a good understanding of what I want to explain.
Let a boy be revolving a ball attached with a thread in circular motion. A ball constitutes of infinite number of particles. So, the particles also move in circular motion with a uniform angular velocity omega along a circle of radius r and center O. Let the time taken by each particle in completing one full circle be t. This is the time period of the particles moving in circular motion. Let us now understand this mathematically.
Now, if capital T is the time period of the uniform circular motion, then omega is equal to 2 pi by capital T. Let xo x dash and yo y dash be two perpendicular diameters of the reference circle. Suppose that at time t equal to 0, the reference particle is at point P naught such that angle POP naught is equal to omega t. From the point P, drop a perpendicular PM to xo x dash and PN to yo y dash. Let OM be equal to x and ON be equal to y. In right angled triangle OMP, angle POM is equal to omega t plus phi. the path followed by the particle during motion, which is used to study simple harmonic motion, is called the reference circle, and the revolving particle is called the reference particle. We can now write cos omega t plus phi equal to Om by Op, which is equal to x by r. This implies that x is equal to r cos omega t plus phi. Therefore, we have x is equal to r cos 2 pi by capital T into t plus phi as equation 1. Also, sin omega t plus phi is equal to mp by op, which is equal to on by op, which is also equal to y by r. This implies y is equal to r sin omega t plus phi. Therefore, we have y is equal to r sin 2 pi by capital T into t plus phi. This is equation 2. The periodic functions are given by the equations ft is equal to a cos 2 pi by capital T into t plus phi as equation 3. ft is equal to a sin 2 pi by capital T into t plus phi as equation 4. These equations represent simple harmonic functions. Since the equations 1 and 2 are identical to the equations 3 and 4 respectively, they also represent simple harmonic motions. The equation 1 gives the displacement of the projection of uniform circular motion along x-axis at any time t, while the equation 2 gives the displacement of the projection of uniform circular motion along y-axis at time t. Therefore, simple harmonic motion may be defined as the projection of uniform circular motion along one of the diameters of the circle. In case the reference particles begins its circular motion from point A, then phi is equal to 0, and accordingly the equations 1 and 2 reduce to x equal to r cos 2 pi by capital T into t and y equal to r sin 2 pi by capital T into t. It's time to conclude the topic for today. Let us do that by quickly summarizing the contents. A motion which repeats itself over and over again after regular intervals of time is called a periodic motion. The regular interval of time after which the periodic motion is repeated again and again is called its time period. Objects which not only return to their original position but continue too far so that they may swing back and forth several times before they come to rest have a simple harmonic motion. Oscillatory motion is the motion that repeats itself over and over about its mean position and remain confined within two extreme positions on either side of the mean position. The displacement of a particle at any instant is the distance of the oscillating particle from its mean position at that instant, whereas amplitude is the maximum displacement of the oscillating particle from its mean position to either of its extremes. The simple harmonic motion executed by any object is given by ft equal to a sin 2 pi by capital T into t plus phi, where ft gives displacement of simple harmonic motion at time t. Simple harmonic motion can be defined as the projection of the object during uniform circular motion along one of the diameters of the circle traced by the object. Let me now ask you a few questions based on today's teachings as to give you a better confidence about the contents of this lesson. The first question is, are all periodic motions oscillatory? And the answer is no. All periodic motions are not oscillatory. The next question is, what is the motion which repeats regularly after equal intervals of time called? The answer to this is The motion which repeats regularly after equal intervals of time is called periodic motion. The next question, what is the maximum displacement from mean position of an oscillating particle called? The answer is, the maximum displacement from mean position of an oscillating particle is called as amplitude. Another question, what is the displacement of a particle executing simple harmonic motion? The answer is, displacement is the distance of the particle at any time from the mean position during simple harmonic motion at that time. ਮੈਨੂੰ ਯਕੀਨ ਹੈ ਕਿ ਤੁਸੀਂ ਅੱਜ ਦਾ ਲੈਸਨ ਬੜੇ ਧਿਆਨ ਨਾਲ ਸੁਣਿਆ ਹੋਵੇਗਾ ਅਤੇ ਇਸ ਦਾ ਪੂਰਾ ਲਾਭ ਲਿਆ ਹੋਵੇਗਾ। ਆਸ ਹੈ ਕਿ ਤੁਸੀਂ ਪੁੱਛੇ ਗਏ ਸਵਾਲਾਂ ਦੇ ਉੱਤਰ ਚੰਗੀ ਤਰ੍ਹਾਂ ਜਾਣ ਗਏ ਹੋਵੋਗੇ। ਧਿਆਨ ਦੇਣ ਲਈ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਵਿੱਚ ਫਿਰ ਮਿਲਾਂਗੇ।